Once again, welcome to our Cooled Care Maths class, and today we are going to learn about vectors. I will simplify it so that everyone can easily understand it, and if you have any question or any comment, just feel free to type it in the comment section. Let us start with the definition. A vector is a physical quantity with both magnitude, which is the size, and direction. Examples can be displacement, velocity, force, etc. Mainly we focus on these examples in physics class, but since we are doing mathematics, we will focus on the calculations. Before we dive deep into vectors, let us start with the vector notation. We want to see how can we write or represent vectors. If we have a vector starting from point A and ending on point B, we can denote that vector as AB in capital letters and then put an arrow on top to show the direction that we are moving from point A to point B. In general, a vector is represented with one single small letter. For example, letter A with an arrow on top show the direction. But since in most cases we will see vectors on diagrams, which will be showing directions, or we are given some background information about the direction of vectors, hence we can also write the letter without an arrow on top. Now for the magnitude or the size or length of the vector, we denote using the modulus sign. It applies in any vector notation that we have talked about. Since the value of the modulus has nothing to do with direction, we can simply represent it with a letter, and we strictly don't put any arrow on top. So, I need you to take note that there is a difference in representing a vector and the magnitude of a vector. The letter for a vector can be positive or negative. That is how we can know the direction. So when the letter is written without a sign, it means it is positive. Then for the magnitude, the letter is always positive, no negative sign. Let us now see how to represent these vectors on a diagram. Let us draw a line, starting from point A and ending on point B. To represent the direction of the vector, we then put an arrow. So now we can clearly know that point A is our starting point and point B is our ending point. And guess what is left? We don't know the size of the vector. So we need to add a letter which shows the magnitude, which is the size of our vector. So if our diagram is drawn to scale, we can see that the length of the light will tell us about the magnitude of the vector. And then the arrow will tell us about the direction of the vector, which will determine whether it is positive or negative. Now let us look at vector rotation. This is simply changing the arrow of the vector so that it points the opposite direction. So back to our line with point A and point B, but this time we want the arrow to point the opposite direction, which means it will point from B to A. This will make point B the starting point of our vector, and point A will be the ending point. And take note that our magnitude is still a value A, but we will add a negative sign to show that the vector is now in an opposite direction. So, from these diagrams, we can see that the vector AB is equal to the vector minus BA. Now, let us move to column vectors and position vectors. From the definition, a column vector is a vector that describes movement displacement in terms of horizontal, x, component, and the vertical, y, component. We can see here how we can write our vector A as a column vector in terms of x and y. Take note that x and y follow the Cartesian plane, where x is positive when we move to the right and negative when we move to the left. Also, y is positive when we move upwards and negative when we move downwards. Now, let us look at the position vector. A position vector is a vector that starts at the origin 0, 0, and ends at a specific point x, y. It is also represented as a column vector, but it is unique in a way that it always starts from the origin. So, suppose we have a point A with coordinates x and y. The position vector will be OA, since we are moving from the origin, O going to point A, and this position vector can be represented as shown here. OA equals A, which is equals xy. Let me represent this on a Cartesian plane. We have this vertical line, which is the y-axis, and the horizontal line, which is the x-axis. The point at which these two lines meet is the origin, O, with the coordinates 0 and 0. Y increases as we move from the origin going upwards, hence it will be positive, and Y decreases as we move from the origin going downwards, hence it will be negative. X increases as we move from the origin going to the right, hence it will be positive, and X decreases as we move from the origin going to the left, hence it will be negative. So, if we have our point A with X and Y coordinates, we can see that this line to the Y-axis shows the Y value, and this other line to the X-axis shows the X value. So, our position vector will be from the origin to the point A, with the value A as previously mentioned, and hence we can represent our position vector as shown. Now let us talk about vector operations, starting with vector addition. When adding two or more vector, we simply add the corresponding X and Y components. For example, suppose we have a vector with A and B, and another vector with C and D. According to the principle, we add corresponding X values, hence A plus C, and also the corresponding Y values, B plus D. Now moving to vector subtraction. When subtracting two or more vector, we simply subtract the corresponding X and Y components. For example, suppose we have a vector with A and B, and another vector with C and D. According to the principle, we subtract corresponding X values, which is a minus C, and also the corresponding Y values, B minus D. Take note, subtracting a vector is the same as adding the negative of that vector. For example, A minus B is the same as A plus negative B. Now let us do an example together. Given two vectors, vector A with 7 and 3, and vector B with 5 and 4. If we do vector addition, A plus B, we get 7, 3, plus 5, 4, which leads to 7 plus 5 and 3 plus 4, and the result will be 12, 7. If we do vector subtraction, A minus B, we get 7, 3 minus 5, 4, which leads to 7 minus 5 and 3 minus 4, and the result will be 2 and negative 1. Let us do another example with a vector diagram. Suppose we have a vector starting at point A, going to point B with value P, and we have another vector starting from point A to a point C with a value of Q. We can see that we can draw another vector from point B to point C, but the value is unknown, so we need to calculate it. So in this case, we have vector AB, which is equal to P, and vector AC, which is equal to Q, and we need to calculate vector BC. BC tells us that B is our starting point, and C is our ending point. So from B, we shall go to A, which means BA. Then from A, we will go to C, which means AC. Therefore, BC is simply BA plus AC. But as you can see, we need BA, but are given AB, which means we are opposing the direction. And whenever there is a change in direction, we have to change the sign of our vector. So BA is equal to negative AB, which is negative P. Therefore, the short and precise answer is BC is equal to BA plus AC, which is equal to minus P plus Q. Or we can write it as Q minus P. Both ways are correct. It only depends on the work presentation that you prefer. Now, let us talk about scalar multiplication. If you multiply a vector by a scalar, some changes will take place. If the number is positive, the vector will change its magnitude, and if the number is negative, the vector will change both magnitude and direction. So, suppose we have our vector with A and B, with a scalar multiple k. We can see that this scalar number will multiply all the components of our vector, which are the x component and the y component. So, we will get a vector with values ka and kb. Now, let us see how the scalar number k can affect the vector in 4 different scenarios. If scalar k is greater than 1, which means it is a positive number, in this case, the magnitude of the vector will increase, or we can say the vector becomes longer or bigger. If the scalar k is greater than 0, but less than 1, this means it is a positive fractional number. Hence, it decreases the magnitude of the vector. If the scalar k is greater than -1, but less than 0, this means it is a negative fractional number. Hence, it changes the direction of the vector and decreases the magnitude of the vector. Lastly, if the scalar k is less than -1, this means it is just a negative number, and it changes the direction of the vector and increases the magnitude of the vector. Now let us do the following example. We are given a vector A, which has 8 and 4, and we are also given 3 scalars, k1, which is equal to 2, then k2, which is equal to -3, and k3, which is equal to 1/2. So, for the first one, k1a, this is equal to 2 times our vector with 8 and 4, which gives us 2 times 8 and 2 times 4. So, our final result is an enlarged vector with values 16 and 8. For the second one, k2a, this is equal to -3 times our vector with 8 and 4, which gives us -3 times 8 and -3 times 4. So, our final result is an enlarged vector with opposite signs, which mean a change in direction with values -24 and -12. For the third one, k3a, this is equal to 1/2 times our vector with 8 and 4, which gives us half of 8 and half of 4. So, our final result is a diminished vector with values 4 and 2. Let us do the example on a diagram. We are given 4 vectors. The first is from O to P. The second vector is from P to Q. The third vector is from O to Q. And the last vector is from M to N. And we are also given that the value of vector PQ is equal to B. And the value of the vector Mn is equal to A. Vector OP is equal to 2Mn. And N is the midpoint of line PQ. Now our fifth requirement is to find the value of vector OQ. So, for us to go to OQ, we start at O, then we move to P, thus OP. And then from P we go to Q, thus PQ. Hence OQ equals OP plus PQ. But we need to find the value of OP first, off which we have been told that OP equals 2Mn, hence OP equals 2A. And PQ has already been given, which is B. Hence OQ equals 2A plus B. Now our second requirement is to find the value of the vector MQ. So from M we go to N, thus Mn. Then from N, we go to Q, thus OQ. Hence MQ equals Mn plus MQ. But we have been told that N is a midpoint, so NQ is half of PQ. Therefore, NQ is half B, since we already know that Mn equals A. Therefore, MQ equals A plus half B. Now, let us move to the calculation of the magnitude of the vector if you are given a column vector. So, if you have a column vector A with X and Y components, then the magnitude is calculated by the Pythagorean theorem. So the magnitude, that is A in modulus, will be equal to the square root of X squared plus Y squared. Suppose we have our column vector with components 3 and 4, then the magnitude of this vector will the square root of 3 squared plus 4 squared, which is equal to the square root of 9 plus 16, which is equal to the square root of 25, which is equal to 5. Now, let us move to parallel vectors. Two vectors A and B are parallel to each other if one is a scalar multiple of the other. So, A equals KB, where K is a scalar constant. If K is positive, the vectors are parallel and in the same direction. If K is negative, then the vectors are parallel but in opposite directions. Suppose vector A has components x1 and y1, and vector B has components x2 and y2. Then the scalar K will be equal to A divided by B, which will be equal to x1 over x2 and should also be equal to y1 over y2. And take note that if x1 over x2 is not equal to y1 over y2, it means there is no value for K, and hence the two vectors are not parallel to each other. Alternatively, we can shift the position of K, then the scalar K will be equal to B divided by A, which will be equal to x2 over x1, and should also be equal to y2 over y1. And take note that if x2 over x1 is not equal to y2 over y1, it means there is no value for k, and hence the two vectors are not parallel to each other. Now, let us do an example together. Given the following column vectors, vector A with components 6 and 4, then vector B with components 3 and 2, to see if the two vectors are parallel to each other, we use our previous formula, A over B, which is equal to x1 over x2, and should also be equal to y1 over y2. So, if we substitute the values, we get 6 over 3 and 4 over 2, and they both give us 2. Hence, we can see that A is equal to 2B, and from this we can conclude that vector A and vector B are parallel to each other, and they are in the same direction, since the value of k is positive. Moving on to the collinear points. Collinear simply means the points lie in the same straight line. If we have 3 points A, B, and C, these points are only collinear if, firstly, AB is parallel to BC, that is, AB equals KBC, and secondly, point B should be a common point. Let me illustrate this on a diagram. Suppose we have a line connecting point A and point C, then point B should be a common point between A and C. So, it should lie on the line, on any point which is between point A and point C. So, suppose AB equals 2A and BC equals A. Then we can see that AB equals 2BC, and also since B is a common point, we can therefore conclude that these 3 points, A, B, and C, are collinear. Let me give you a bonus point about ratios on a line. Suppose we have a line AB with a point P in between, such that it divides the line AB to AP and PB in ratio 2 as to 3. So, the first case is, if we consider AP and PB only in relation to each other, we simply use the same ratio 2 as to 3, hence, AP equals 2 over 3 PB, and PB equals 3 over 2 AP. The second case is, if we consider AP and PB in relation to the full line AB, we have to use the total ratio, which is 5, hence, AP equals 2 over 5 AB, and also AB equals 5 over 2 AP. Also, PB equals 3 over 5 AB, and AB equals 5 over 3 PB. Now finally, let us do an example from a past examination paper and apply the principles that we have learnt. So we are given a vector PR with value B, vector PQ with value A, M, and N are midpoints on PQ and RQ. Then we have two lines which meet at point X, such that the ratio of PX as to XN is 4 as to 3. Let us now answer the following questions, whereby we need to express all those vectors in terms of A and B. So going to the solutions, let me put the diagram and the description on the side to make it easy to follow my working. Starting with the first vector QR, this is simply QP plus PR, since we are starting at Q, then to P, then to R. So, since we are opposing PQ and following PR, hence it will be minus A plus B. And we can also rearrange it to be minus A. Then for the second question, we need to find QN, but we have been told already that N is a midpoint, which means QN is half of QR. Hence QR equals half of B minus A. Going to the third solution, we are required to calculate Pn, and it is clear that Pn equals PQ plus Qn. Hence it is A plus half of B minus A. If we rearrange, we get a minus half A plus B, which will give us half A plus half B. We can also factor out the half and put a plus B in brackets. Then finally our last task is to calculate Px, since we are given the ratio 4 as to 3, and we have the vector of the full line Pn from the previous working. We need to use the total ratio, since we are calculating based on the full line. So, our total ratio is 4 plus 3, which is equal to 7. Hence Px is equal to 4 over 7 times Pn. If we substitute, we get 4 over 7 times half of A plus B, which will give us 2 over 7 times A plus B. Thank you so much for watching. I hope this video was very useful to you. And once again, if you have any comment or question, just feel free to type it in the comment section. And don't forget to like, share, and subscribe. I wish you all the best.